Welcome to Math 2318, Section 4.4. We are given the coordinates of a vector relative to a particular basis, and we'd like to know, well, what is the coordinates of this vector in the standard basis? So in question 1, we are given two basis vectors, b1 and b2. We are given the representation for vector x relative to that basis as 3, 4. Well, the question is, well, what are the coordinates of that vector relative to the standard basis for R2? Well, we simply form PB, which is we take B1 and B2, put them in the columns of our 2 by 2 matrix. It acts on the vector, its representation with respect to that basis. We do the matrix multiplication, and that gives us what would the vector representation be for that vector relative to the standard basis. All right, we continue that process in question 2. We have something now in R3. We have B1, B2, B3. So we form PB, which simply puts them in the columns. We are acting on vector x relative to that basis, which is 3, 1, minus 1. We perform the multiplication, and we see that relative to the standard basis, that same vector would be represented as minus 9, 14, and 11. So different bases give us a different way to represent the same vector. All right, in this case, I've got vectors b1 and b2. We have x, so this is relative to our normal basis. We'd like to know, well, what is its representation in terms of b1 and b2? So we simply form PB, which is our b1 and b2. We know that a times x relative to b should give me that vector, minus 13, minus 8. So we simply solve for, well, what is the x relative to b that would do that? So we do our row operations. I switched out the two rows and divided this row by minus 2. So now I'm going to use the 1 to make a 0. Did that. Divide this particular row by minus 3 and then make a 1 above it. So we see that relative, so xb, so this is x relative to b, is 2 minus 1. All right, this change of coordinates is simply what we've been doing. So if here's my basis vectors, then to form PB, you simply put them in the corresponding columns. In question 5, we repeat that same process, but now we're in R3. All right, B1, B2, and B3. Question 6, we have a basis relative for P2, the set of all polynomials of degree 2. So this is our basis. We have our coordinate vector, which looks like the following. Now, this is relative to the standard basis for P2. Remember that the standard basis looks like 1t squared. So we want to figure out, well, what does it look like relative to this basis? So what I need to have happen is C1 times that B1 plus C2 times B2 plus C3 times the B3 to match up with my P of T that was given. So we distribute C1, C2, C3, and then it's just a question of matching things up. I've got a constant which has to match up with minus 1. I've got this term which must match up with minus 12, and this term which matches up with minus 6. So that gives me a set of equations which I turn it into a matrix to solve. So I'm going to use this 1 to make a 0. Did that. Let's see, I see I've got a 1 here, so I'm going to divide this row by negative 1 and then swap it out. Okay, got that. I'm going to use it to make a 0. Alright, so that looks good. In row 3, I'm dividing it by negative 1 and then using it to get rid of that 1. And so what we see is that if I take minus 3 times their B1, 5 times B2, plus 2 times B3, it would give me my P of T. All right. What we have here, B is the standard basis for P3. P3 is all third degree polynomials. Standard basis 1t, t squared, t cubed. So I want to figure out, are these three vectors linearly independent or not? So what would this vector be relative to the standard basis? So I've got a 1. It doesn't have any t term. It has a minus 2 for the t squared and a minus 1 for the cube. We do this for all three of them. For the second one, let's see, there's no constant. That's 0. A 1 for the t. There's no squared. And I do have a 4 for the t cubed. So we do the same thing for the last one. We put them in a matrix representation of their coordinates, do row operations, and what we see is we do have a pivot position in each of the columns. So the columns are linearly independent, and so the polynomials are linearly independent. All right, let's see. In this case, we have P1, P2, P3. We want to show that they form a basis for P2, set of all second degree polynomials. Well, so what are their coordinates relative to the standard basis? Well, let's see. So P1, I've got a constant, 0 for the t, and 1 for the t squared. So do that for all three of them. Put them in our matrix. We see what happens, and it is row equivalent to the identity matrix. Therefore, by the invertible matrix theorem, it does form a basis for R3. Therefore, because of the isomorphism between R3 and P2, it is invertible, all of that, it spans, so the polynomials do form a basis. And so let's see, we've got P1, P2, P3. I want to find a particular Q, given that the Q is of this form relative to B. So what did I do? I took my PB, I multiplied by its coordinates, which are minus 3, 1, and 2, to give me the coordinates relative to the standard basis for P2.